Greetings. Today we're going to talk about acceleration, forces, mass, Newton's law of gravity, energy, mechanical energy to be precise, power, and we're going to answer some questions. So, greetings. This is Akamaro from the Portland, Oregon Temple, and we're just going to go over some topics about acceleration and physics. So, okay. So, at first I drew this train with no windows in it, and this is to represent that if you've ever been in a train or a car and a moving object that's going at a constant velocity, um, it really feels like you're actually not moving at all. Now, maybe let me rephrase that. Say that you're in this train and there's no windows, right? And and you're just sitting down, and the train is moving at some speed. Okay. Now, if it's moving at a speed, say 10 miles per hour, you won't know the difference if the train was moving at that speed or if it was just not moving at all, if it was at rest. Again, like if this goes back to Galileo and Newton, where you can't make an experiment to really tell the difference between an object if you're inside a system that's moving at constant velocity or how to tell if it's at rest. To yeah, imagine like for example right now, even like according to physics, Earth is moving at a certain speed around the sun and it's rotating, etc. But we don't really feel it. Like we think we're at rest, right? We don't think we're moving at this like incredible speed across the space and time. So that's just something I wanted to let you know. Maybe it's obvious, but it connects with acceleration because the only way we actually feel us speeding up or slowing down is when there exists acceleration, right? So when there exists a change in velocity. So for example, if you're in the train and the train stops all of a sudden, you're gonna feel that, right? You're gonna feel like the you're gonna feel the weight of the deceleration. And similarly, if you accelerate, you're gonna feel that too. Or if you're in I don't know in if you're in a festival and going on a ride or something like that, you might feel like you're dropping down, right, from this like amusement park. Um, well, anyhow, and the way we calculate acceleration is by taking by comparing two velocities, right, over a certain time. So I have my final velocity, my initial velocity, and then I compare it over the time it takes them to go from my initial to my final. Okay? Now I have my Minecraft character here. He's walking at 5 miles per hour, and after a quarter of an hour, he starts running at 20 miles per hour. Now I don't know if Minecraft characters actually run, but needless to say, this is an example. So we want to calculate the acceleration of this Minecraft character, right? So our final velocity is 20 miles per hour, and our initial velocity is 5 miles per hour over a period of a quarter of an hour. Now this becomes 15 divided by a quarter becomes 60 miles per hour squared. This is important because this squared actually represents acceleration, right? So it would be distance over time squared. Whatever that unit of time may be, hours, minutes, seconds, but that unit of time would be squared. Okay? Okay. And now what would like movement look if what would movement look like if, say, for example, a ball or an object was moving at a constant acceleration, right? This is a topic in your physics class that you probably went over in kinematics equation, but just to reiterate, um, if I have an acceleration of 1 meters per second squared, what does that really mean? Now, let me compare that to maybe, for example, velocity of 1 meter per second. What this is telling us is that after 1 second, right, I will move 1 meter. And after 2 seconds, I will move 2 meters, and so forth. In the same way, from acceleration, if my acceleration is 1 meter per second squared, after 1 second, my velocity will be 1 meter per second. After 2 seconds, my velocity will change to 2 meters per second. It will increase, correct? So maybe in a more picturesque way, let's say we have this ball and it starts at time 0. Let's say it starts with a velocity of 1 meter per second, right? Now, after 1 second, t equals 1, its velocity is going to increase by 1. So my new velocity will be 2 meters per second, and so forth. As you can see here, after t2, it increases to a velocity of 3 meters per second, and so forth. 4 meters per second and 5 meters per second. Okay? And so this comes to, this actually relates to continuous change in velocity. As you can see here, like, even though this velocity represents at t equals 0, what would happen at t equals 1/2? Well, at t equals 1/2, given that my acceleration is 1 meters per second squared, my velocity should be 1/2 meter per second. I hope that is clear. I hope that's clear why. And so forth, right? So if I were to have, excuse me, this would be 1 meter per second. My velocity should be 1 meter per second plus 1/2 meter per second. That's because we started with 1 meter per second. And we added 1/2 meter per second after 1.5 seconds, right? Okay, excuse me about that. Now, what about continuous change of velocity? Change of velocity will be continuous. That is what we experience when we see an object fall. So gravity is 9.8 meters per second, and this is acceleration due to gravity. Acceleration due to gravity. And this acceleration due to gravity continuously changes the velocity of an object that is falling towards the Earth. So just to make it maybe more visual, say I'm holding this ball, right? And at time equals 0, my velocity will be 0 meters per second, right? It's not moving. Now I let it drop, and after 1 second, my velocity will change to 9.8 meters per second. If I let it drop 2 seconds, then my velocity will change to 19.6 meters per second. And again, just to reiterate what happens at t1/2, this would be 9.8 over 2, which is 4.9 meters per second. Okay? So that is, so at every point in time here, at every point, there's going to be a different velocity. Okay? Now, there's an interesting fact that, say, for example, you were to compare a wooden, say, for example, you were to compare a wooden ball to, for example, a lead ball. Do you think these will fall differently? Like, would the wooden ball fall slower than the lead ball? Well, of course, you might think that because, like, the lead ball, if you were to hold it, right, it feels heavier than the wooden ball, right? You assume that the lead ball should fall faster than the wooden ball because it feels heavier. However, that is not the case, actually. If you were to drop the lead and the wooden ball, they will fall at the same rate. So after t equals 1 seconds, their velocity will be 9.8 meters per second. Now t equals 2 seconds, the velocity will be 19.6 meters per second. Now, again, we're making the assumption that they have the same size and the same shape, etc. Now, the reason why this might not happen with, like, for example, a piece of paper and a in the wooden ball or lead ball is that the piece of paper has drag, has air drag, meaning that because of the air molecules that are in it, the piece of paper will start to like fall in this like weird shape, right? It won't fall straightly down because of all the air that's around it. But if you were to make a vacuum, in other words, take out all the air from a system and have a piece of paper and a lead ball, they will both fall at the same speed. And you can actually see this. There's some videos online um, of like free fall in a vacuum, like having a feather and I think like some other object. It's pretty interesting. So so it doesn't matter. So the acceleration of an object due to gravity doesn't depend on their weight, their shape. Um, it's just like any object will fall towards the Earth at at an acceleration of 9.8 meters per second squared, which is a very interesting fact. I know I find it very interesting. Um, yeah, so that's one thing to keep in mind, and we will come back to this. We will come back to this, but I want to talk about a slightly more complicated situation. Again, I will assume that you've learned about vectors and stuff in your physics class, and doing subtraction of vectors, etc. If not, you feel free to skip this part, but I thought it might be fun to explain it. So assume you have like a ball, and the ball is moving along this path, right? Now, what we're gonna do is use these arrows to indicate the velocity of this ball. Now, the length of this arrow represents how fast it's moving. Say, for example, if the length of this arrow was 1 centimeters, then that would be equivalent to 1 meter per second, right? If it was 2 centimeters, then that would be 2 meters per second. And where this arrow is pointing to, if it's pointing to the left, to the right, northeast, etc., that would be the direction in which the object is moving in. Okay? So, one interesting fact is that the ball that's going along this path, its velocity vector will always be tangent to the path. Um, this you might learn more in a calculus class, like vector calculus, etc. But it's an interesting fact to have nonetheless. And now the acceleration vector, now this will be a vector instead of just a number, will be in the direction, will be the difference between two velocity vectors over time, right? And this is kind of like interesting fact. So you can have all these arrows along your path that would represent like acceleration, for example. Yeah, something along those lines. Again, I'm not a great drawer, but just to give you a sense of this. And why do I say this is because we can have things that are moving in also just three dimensions. It could be moving around in 3 dimensions, and you can have these arrows in 3 dimensions. And we can actually calculate the acceleration, we can figure out how it's moving, etc., and we can use computers to do that, to simulate that. So I think that's just like a cool aspect of it. So we can extend this whole like notion of acceleration to other dimensions. And I hope that's clear with acceleration. Again, the topic of acceleration becomes a lot easier if you know calculus. But I think for now, I think that's a good start. Now, we're going to talk a little bit about forces and we're going to go back to acceleration. So from Newton's second law, we have F equals m times a. It might be Newton's second law. Again, to the best of my memory, it's Newton's second law. So the force equals mass times acceleration. Now, the question is, why do we have this? This looks very abstract, maybe. Maybe if you've first seen this, if it's your first time you see this, it might look a bit abstract. It's like, why do we have mass and why do we have acceleration? Well, let's go back to this example that we had here. So remember how we were talking about how like two objects that might feel that they weigh different, right? Like a wooden ball and a lead ball, they feel like they weigh different, but their acceleration towards Earth is the same, right? So what is different? Because if this ball is falling, right, and you're below it, if this ball is a wooden ball, that's not gonna hurt that much. But if it's a lead ball, it might give you a concussion, right? So even though they're having the same acceleration and they have the same final velocity, the force in which it hits your head, or like the effect that this ball has on your head, is actually, it depends on, right, like what object you're using, a lead ball or a wooden ball. So that's an important distinction. So the difference between objects is going to be their mass. Okay? So what we have here is a wooden ball might have a mass of, say, 5 kilograms, or maybe even smaller, maybe 1 kilogram, right? Whereas a lead ball might have a mass of, I don't know, 10 kilograms, or maybe more. So, as you can see, their mass is different. And that is what causes, for example, force, that's the force that this ball has on your head to cause a concussion to be greater or less. So if this mass increases, say if it goes from 5 kilograms to 15 kilograms, that's going to create a greater force, which could lead you to be a concussion. Now this G is for acceleration, right? We still have the formula F equals m times a. So that is one of the reasons. No, the big question more so is how to measure mass. Now that could be a bit complicated depending on how you want to answer it, but I could explain to it if you so desire in a later video, but for now let's just go with the flow of different objects have different masses. So we have this notion of force equals mass times acceleration, and again, we're using acceleration g here if the object is falling. It's on free fall towards the Earth. So, and moreover, like in general in physics, we restrict our knowledge to what we can measure, right? We don't just assume things that we can't measure. And so from that point of view, we can really measure the change of velocity of an object, in other words, acceleration. And we can measure the object's weight compared to other objects. For example, if we have a kilogram of something, a kilogram of a block, a metal, we can compare that using a scale with another object, say like a wooden ball, right? And then we can combine these two facts. We can combine these two like concepts to create this like sort of physical framework, mathematical framework, in which we define this notion of force, right? Now, for example, just to reiterate, if we have like a lead ball of say 5 kilograms, and now I had a wooden ball of 1 kilogram, right? To have the same force that this lead ball has, compared to this wooden ball, I would need this wooden ball to be 5 times as larger, right? Because then it will have a mass of 5 kilograms, which would be comparable to the mass of the lead ball. Okay, so then if we were to let him fall and hit my face, it would give me the same level of concussion. I know these examples are terrible, um, but they would have the same amount of force. Okay, and again, if you have examples or like questions to talk about, for example, if you were to give it like the mass of an object is 15 kilograms and is falling to the earth, right? Then you can assume that the acceleration is actually 9.8 meters per second squared, right? And so then you can calculate the force, which is 15 kilograms times 9.8 meters per second squared. And that'll give you, that's approximately 150 newtons. Now, what is Newton? Well, a Newton is an abbreviation for kilograms times meter per second squared. So we're just combining these like units into another unit, which we call newtons. Okay? And similarly, if you're given like, say for example, some object has a certain, you know, there's a certain force of 10 newtons, and then there's like a mass, an object has a mass of 10 kilograms. What is the acceleration this object had, right? Then we could just use the formula of F equals m times a, right? We can solve for A equals F divided by mass, which gives me 10 newtons divided by 10 kilograms, okay? Which would be, my acceleration would be 1 meters per second squared. And similarly, you can do the same for mass if you're getting force and acceleration, right? If you're given force of an object, acceleration of an object, and you're asked to find its mass, you again would solve for mass, which would be force over acceleration. So I think most of this is pretty straightforward. And so that's how you use force for like a brief example. Okay, so now we're going to go to Newton's law of gravity. So what is Newton's law of gravity? Well, before we talked about F equals m times a, right? Mass and acceleration. However, that doesn't really apply to everything. Like, what I mean to say is that how do we consider two objects that are like in space, like say two stars, and how does the force of one star affect the other force of another star, right? If you consider this equation, mass and acceleration, this equation doesn't have anything to do with the mass of the other star, or like whose mass are we supposed to use here, and what gravity, what acceleration should we use here? Is it the gravity of, let's say if we were comparing the Earth and the Moon, do we use the gravity of the Earth or the gravity of the Moon? Like, so we need a broader function, a broader function, one that relates the masses of these two objects, m1 and m2, and their distance, and the distance between them. This would be r, right? Okay, and Newton was trying different equations out, and one of the ones that really stuck was this, right? Where g is actually a constant, is a small constant that we use. So for every calculation, you would use the same g. And now you just plug in the mass of an object, the mass of the other object, and the distance between them, right? And then you square it. So that is the equation of Newton's law of gravity. And what's really cool is that how does this relate to the equation of force equals mass times acceleration, right? How does that connect with this equation, right? Because we're still measuring force, right? So, okay. let's compare what we would say like an object going free fall or falling towards the Earth, right? We have this big mass, the mass of the Earth, and this should be actually like a dot, right, or even smaller, of the mass of this other object, right? Which could be, let's call it this a bowling ball. Okay. Now the force on the bowling ball, if we were to just use the normal equation that we would have before, the force due to gravity, according to physics, would be the mass of the bowling ball times g, right? But according to physics, the force that the bowling ball would experience would be, according to physics too, the force would be the constant g times the mass of the Earth divided by the radius between the center of the Earth towards the center of the bowling ball times the mass of the bowling ball, right? But these two forces are the same, so they must be equal to each other. So the constant g times the mass of the first times the mass of the second divided by the radius squared is the same thing as m2 times g. Now, what we can do is cancel these m2's, and what we're left with is this equation down here. G equals n1 over r2. So we have a way to calculate the gravity of different. So this would be a way to calculate the gravity of an object, the acceleration of an object, right? So let's calculate Earth's gravity, right? Why not? So we have the mass of the Earth, which is 5.972 times 10 to the 24th kilograms. And the radius of the Earth is 6.378 times 10 to the 6 meters. And we plug this into our equation, right? Again, we have to use this constant, g, into our equation here. Plug it in here. We plug in the mass of the Earth here, and we plug in the radius. And we square it, right? And that gives us an effect due to gravity of 9.79244 meters per second squared, which is about 9.8 meters per second squared. Yeah, and so that's really close, right? And so we calculated what gravity is. Okay, let's do a couple more calculations. What about the moon? Now again, I did the same thing. I had this constant g. Now I have the mass of the moon, and then I have the radius of the moon, and then I square it. And that gives me a value of gravity of 1.6235 meters per second squared. Okay, so that's what the gravity, this is the amount of gravity that would be on the moon. Okay, okay. Now computing bowling ball's gravity. Now let's say I have a bowling ball, and it's like before we calculate the gravity of the Earth. Now let's calculate the gravity of the bowling ball. So in the same way, we would have the mass of the bowling ball, the radius of the bowling ball, we will square it, and then we can calculate it. So we have the constant g, big G. Now, bowling ball is about 5 kilograms, and its radius is about 0.12 meters. So we square that, and what we get is 2.3159 times 10 to the negative 8. So this effect of gravity, so a bowling ball does have gravity, but it's really small. Like, you can hardly feel it. But that is the effect of, that is the attraction that this bowling ball would have towards any other object. So this is the effect of gravity that the Earth has, that the bowling ball has on Earth, which is kind of interesting to think about. Okay, and that's about what I have to say about Newton's second law, Newton's law of gravity. Again, you can be giving you can be given like different problems in school. Say, for example, the force is 100 newtons, right? Here. And then you're given gravity, right? You already know what G is, that's given. And you have two objects, right? Say, for example, you're given the radius, maybe this is 1,000 meters, and you're given the mass of another object, say this is 15 kilograms, right? So you're given 15 kilograms divided by 1,000 meters squared. And now you have to solve for the mass of the second one, right? And this is simply like just doing algebra, right? You just pass the radius to the other side. G, you divide by G, you divide by the mass of 15 kilograms, and you're left with the mass of the second equals 100 newtons times 1,000 meters squared divided by G divided by 15 kilograms, and that's it, right? And then you just put it into your calculator, and that's what you would have. You would solve. Now, say for example, if you were solving for radius, you were given everything else, the force, the mass of the second. What is radius, right? Well, you can do that too, right? So you would move this to the top, right? So what we have is force radius squared equals G m1 times m2, right? And now you divide by force. So you have G times n1 times m2 divided by the force. And now what we can do is take the square root of them both. So then what you're left is R equals the square root of G times n1 times m2 divided by force. Okay? And so that's in essence how you would do these problems. I hope this helps, makes things clear. A lot of it is just like solving for one variable and then plugging in the variables that you've been given. Okay? All right.